Session is being recorded. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will start explaining chapter 2 in the wireless communication and networks, which is about wireless fundamentals. So this is the layout of chapter 2, which is about wireless fundamentals. It's focused on understanding basic wireless theory, understanding the frequency, wavelength, phase, understanding the radio frequency power and dB, and the carrying data over a radio frequency signal, OFDM, MIMO, etc. In addition to that, we will explain how to use multiple radios to scale performance. After that, we will have a practical lab session, which is about radio frequency mathematics and how to calculate the EIRP. Let us start. First of all, what is wireless communication? Who can tell me what is wireless communication? We have explained in the previous lecture that wireless signal travels as electromagnetic waves through the air from sender to receiver. So the wireless signals travel between the mobile station and base station as electromagnetic signal, which consists of electric field and magnetic field. And these fields are perpendicular to each other, so there is a right angle between the electric field and magnetic field. There is a right angle between the electric field and magnetic field. For this reason, we call it electromagnetic. Furthermore, we mentioned that wireless communication, it is the transfer of information between two or more points that are not connected by an electrical conductor. The transfer of information between two or more points up to here is communication. But when we say that are not connected by an electrical conductor, this is wireless communication. So the sender is a transmitter that sends an alternating current, AC current, into a section of wire, an antenna. After that, this sets up moving electric and magnetic fields that propagates out and away from the antenna as traveling waves. So it starts from the transmitter that sends AC current into the wire of antenna, and this sets up moving electric and magnetic fields to the base station. So the electromagnetic waves, the electric and magnetic fields travel along together. So the electric field travel with the magnetic fields, and they are always at right angles to each other. So the angle between the electric field and magnetic field is 90 degrees. The signal must keep changing or by alternating, by cycling up and down to keep the electric and magnetic fields cycling and pushing ever outward. So the electromagnetic wave don't travel strictly in a straight line. The wireless signal that travels between the mobile station and a transmitter and another mobile station, which is the receiver, it does not travel in a straight line. It does not travel in a straight line. It keeps cycling and pushing ever outward. It cycles up and down, up and down. So in free space, the electromagnetic waves expand outward in all three dimensions. In 3 dimensions. Also, in free space, the speed of the electromagnetic signal is the speed of light, which is 3 times 10 power 8 meter per second. This is the speed of electromagnetic wave in vacuum. So the electromagnetic waves, they are defined by this equation: A equal cosine 2 pi ft plus epsilon. A is the amplitude of the electromagnetic wave. F is the frequency, how many cycles per second, and epsilon is the phase. So these are the three characteristics of the electromagnetic wave. A is the amplitude of the wave, F is the frequency, and epsilon is the phase. I will show you now a MATLAB file that shows you the difference between electromagnetic waves having different amplitude, different frequency, and different phase. Let us start. Here you can see an electromagnetic waves, 3 electromagnetic waves having different amplitude. So both all electromagnetic waves, all the three, they have the same phase. They have the same frequency. Same phase and same frequency. But the difference here in amplitude. You can see the green electromagnetic signal is having the highest amplitude. The red electromagnetic signal have the second highest. And then the blue electromagnetic signal has the lowest amplitude. So these three electromagnetic waves, they have the same frequency, same phase. There is no shift between them, but the amplitude is different. Another figure, it will show you the difference in frequencies. So here we have two electromagnetic waves, a green one and a blue one. Both they have the same amplitude, but the difference in frequency. Which frequency is higher? The frequency for the green electromagnetic waves. Why? Because it is making more number of oscillations per second, more number of cycles per second, up and down, up and down. It's the cycle is from this peak to is one up and one down, one cycle up and one down. This is the cycle. Top. Which signal is making more cycles per second? The green, because it is oscillating more than the blue signal. But which signal has the highest wavelength and lambda? The blue signal. Why? Because the lambda is the physical distance. It's the physical distance from this peak to this peak. From the peak 1 to peak 2. This is lambda. It's the physical distance between peak 1 and peak 2. This is the wavelength. So for the blue signal, it has higher wavelength, higher lambda, whereas the green signal have lowest lambda, lowest wavelength. So we conclude that as the frequency increases, like in the case of the green signal, wavelength decreases. As the frequency increases, wavelength decreases. And as the frequency decreases, wavelength increases. And here is a third figure that shows three electromagnetic waves. Here, how many electromagnetic waves? Three. The three of them, they have the same amplitude and same frequency and same wavelength, lambda. But there is phase difference between them. You can see there is shift between the green electromagnetic wave and the blue and the green and the red one. There is a shift between the red electromagnetic wave and the green one. There is a shift between the green electromagnetic wave and the blue one. So this shift, phase shift, is measured in radian. This is what we called here epsilon. Epsilon. So epsilon is the phase shift for the electromagnetic signal. A is the amplitude and F is the frequency. And in general, electromagnetic wave is expressed by this expression, A cosine 2 pi ft plus epsilon. The electromagnetic waves, they are synchronized oscillations of electric and magnetic fields, as we have explained before. So they are produced at different wavelengths or frequencies. As the frequency increase, wavelengths decrease, and the opposite. As the wavelengths increase, frequency decrease. In vacuum, the electromagnetic waves travel at the speed of light, which equals 3 times 10 power 8 meter per second. And these are the properties of the electromagnetic wave. When we mention the property of electromagnetic wave, we mean the amplitude, frequency, and phase. So, isotropic antenna. Isotropic antenna. What is isotropic antenna? The isotropic antenna is a theoretical antenna that radiates power uniformly in all directions. So it is theoretical antenna, not real antenna. It is theoretical antenna that radiates power, as you can see here in this figure. It radiates power in all directions. This is the isotropic antenna It is radiating power in all directions. So this is theoretical. It is not real. It radiates power uniformly in all directions in 3D space, like a perfect point source. So it has no preferred direction. The isotropic antenna has no preferred direction. I cannot say that isotropic antenna has direction toward the right or the left. No, it has no preferred direction. It radiates power uniformly in all directions. So it is used as a reference model for comparing real antenna gains. So if I say that I have antenna, its gain is 10 dBi. When I mention dBi, I mean it has 10 dB gain with the reference to the isotropic antenna. So the isotropic antenna is a reference. What is the gain of isotropic antenna? Is 0. The gain of isotropic antenna is 0. When I mention that any antenna has a gain of 10 dBi, it means it has a gain which is equal to 10 dB compared to the isotropic antenna. This is a reference. This is theoretical antenna. This is not physical antenna. This is the reference. Okay? So it is used as a reference for comparing real antenna gains measured in dBi, which equals gain relative to isotropic antenna. So it does not exist physically, but it helps engineers benchmark how directive or efficient a real antenna is. This is the isotropic. So the waves produced from a tiny point antenna expand outward in a spherical shape. The waves will eventually reach the receiver, in addition to many other locations in other directions. So, figure 2, it shows a simple idealistic antenna that is a single point which is connected at the end of a wire at the sender. At the receiving end of a wireless link, the process is reversed. As electromagnetic waves reach the receiver antenna, they induce an electrical signal. So, I need to repeat and focus that the isotropic antenna is considered as a reference for other antennas. So its gain is 0. First, its gain is 0. It propagates power in all directions in 3D. And when we say that any antenna has a gain of 10 dBi or 20 dBi, which means this antenna has a gain of 10 or 20 with the reference to this antenna. So this is a reference. This antenna, which is the isotropic, is used as a reference model for comparing the real antenna gains. Electromagnetic wave frequency. What is the frequency? What is the definition of a frequency? One fundamental property of wireless link is the frequency of the wave. The frequency, it is the number of oscillations or number of times the signals make one complete up and down cycle in 1 second. How many cycles the frequency is making per 1 second? This is 1 cycle, right? From here to here, this is 1 cycle. Then this is the second cycle. Then this is the third cycle. And this is the fourth cycle. So it is making 4 cycles per second, which means that the frequency equals 4 cycles per second, or in other words, 4 hertz. So hertz is the unit that measures the frequency. The frequency is measured in hertz. The frequency is measured in hertz. The unit of the frequency in hertz. What is hertz? How many cycles I am doing per second. So a hertz, it is commonly used a frequency unit and corresponds to the number of cycles per second. In figure 3, suppose that 1 second has elapsed as shown. During that 1 second, the signal processed through 4 complete cycles. So within 1 second, I have 4 complete cycles, which means that the frequency equals 4 cycles. per second, or 4 hertz. So a cycle can begin as the signal arises. Here the cycle begins from the center line and falls through the center line and rises again till here. So here it rises, then it falls down, then it rises again. Here it completes one cycle. It completes one cycle to meet the center line. So the kilohertz, it equals 1000 hertz. When we mention the frequency of a signal is kilohertz, 1 kilohertz, which means 1000 hertz. When we say 1 megahertz, it means 1 million hertz. When we say gigahertz, it is 1 billion or 10 power 9 hertz. So what is wavelength? Wavelength is another important property of electromagnetic wave. So we explained the frequency. Now we need to define the wavelength. The wavelength, it is a measure of the physical distance that a wave travels over one complete cycle. It is a measure from here to here, physical distance that a wave travels over one complete cycle. Or you can measure from peak to peak. It's the physical distance from peak to peak. This is lambda also. Wavelength is usually designated by the Greek symbol lambda. When we mention lambda, we mean the wavelength. So wavelength decreases as the frequency increases. You can see here frequency is increasing. Number of cycles per second is increasing, which means lambda will decrease. As the frequency increases, lambda decreases. As the wave cycles get smaller, they cover less distance. So once the frequency increases for any signal, it means that it does not cover a huge distance. It covers less distance. It does not travel too much. So regardless of the frequency, RF waves travel at a constant speed. Why? Why regardless of the frequency, RF waves travel at a constant speed? Because C equals lambda F. C equals lambda times frequency. C equals lambda times the frequency. How much C equals? C equals 3 times 10 power 8. This is constant, fixed. This is the speed of electromagnetic wave in vacuum, which equals the speed of light, which equals C and equals 3 times 10 power 8. So this is constant. So if lambda increases, frequency will decrease. If a frequency increases, lambda will decrease. So they are inversely proportional to each other. Frequency and lambda are inversely proportional to each other. In vacuum, radio waves travel at exactly the speed of light. In air, the velocity is less than the speed of light. So you can see from these three figures, as the number of cycles per second increases, as the frequency increases, lambda will decrease. So this is the electromagnetic wave. Here we can see that we have two signals, one in line and one in dashed line. Both are in phase, both have the same phase. So the phase of a signal is a measure of shift in time. The phase of the signal, it is the measure of shift in time. How much shift I have between these two signals? There is no shift, so they are in phase relative to the start of a cycle. So when two identical signals are produced at exactly the same time, their cycles match up and they are said to be in phase with each other. If one signal, like you see here, is delayed from another one, so there is delay between the two signals, the two signals are said to be out of phase. Phase difference between them. There is a phase shift between them, right? there is a phase difference between the first signal and the second signal, so they are out of phase. Signals that are in phase tend to add together, so these signals, they strengthen each other. The signal will be stronger because they are in phase and they are adding to each other. Here the signal is stronger. Whereas the signals that are 180 degrees out of phase, if there is 180-degree shift between each others, they will cancel each others. They will cancel each others. Now we will speak about the FDMA. What's the FDMA? The frequency spectrum divided into frequency bands or channels. So each user can send on a frequency at the same time. In TDMA, each user used to send at different time for the signals not to have interference, to avoid interference between signals. But in FDMA, they can send at the same time, no problem. These 4 users that can send at the same time. These N users can send at the same time, but every user is sending at a different frequency. User 1 is sending a signal at frequency 1. User 2 is sending frequency at F2. User 3 is sending frequency at F3. User N is sending frequency at Fn. So each user allocated a different channel band. Each user assigned a fixed frequency band. Unused transmission time and frequency bands go idle. The unused transmission time and frequency bands go idle. So the idea of FDMA is that I have multiple users and each user is using a frequency to transmit on it. Even if they are sending at the same time, it's not a problem, but everyone has his own frequency band, his own channel. You can see here from the figure, if these 2 users are sending at the same frequency, F1, interference will happen. What is interference? It is a phenomenon in which the 2 waves superpose to form a resultant wave of greater or lower or same amplitude. When interference happens, the signal, if they are in phase, when interference happens, the 2 waves will superpose to form a resultant wave of a greater, lower, or same amplitude. But this is not the scenario that we need. We need a scenario where a user uses his own frequency, which is different from the frequency used by other users. So here we have 2 users. They are sending at different frequencies. Interference will not happen because the channel of this user, the frequency of this user, is different from the frequency of this user. Here interference will not happen. Whereas in this scenario, they are using the same frequency and this will result in interference. So the idea of FDMA is to allow multiple users to share the same communication medium. So in FDMA, which stands for frequency division multiple access, it divides the frequency spectrum into frequency bands or channel, and each user is assigned a fixed frequency. Why? To avoid interference. Like in this scenario, user 1 uses F2, frequency 2, user 2 uses frequency 3. So what happens when a frequency band is unused in FDMA? The unused frequency band goes idle. The unused frequency band goes idle. So this is an important slide which is about channels and bandwidth. This slide is about channels and bandwidth and the frequency spectrum. You know, in the frequency spectrum, as you can see here, we have different frequencies from frequency 0 to frequency 10 power 22. From frequency 0 to the frequency 10 power 22. So this is here you have the subsonic. Subsonic, this sound we cannot hear. Then this is the sound. Usually it is between 20 and 20 kilohertz. The sound that we hear is usually between 20 and hertz and 20 kilohertz. Then here you have the range of the radio frequencies. The range of radio frequencies, which includes the low frequency radio, AM radio, FM radio, microwave, radar, and it also includes the 2.4 gigahertz and 5 gigahertz frequencies. These two frequencies are used in wireless, in addition to the new one, which is the 6 gigahertz frequency. So three frequencies are used in wireless: the 2.4 gigahertz, 5 gigahertz, and 6 gigahertz. And the three of them are in the radio frequency spectrum. After that, we have the visible light, ultraviolet, X-ray, gamma ray, cosmic rays. But in this chapter and in this course, our focus is on these frequencies: 2.4, 5, and 6. So this figure, it shows a simple representation of continuous frequency spectrum ranging from 0 to 10 power 22. At the low end of the spectrum are frequencies that are too low, here, subsonic, which are too low to be heard by the human ear, followed by audible sounds, usually from 20 hertz to 20 kilohertz, audible sound. The highest range of frequencies contain light, ultraviolet light, followed by X-rays, followed by gamma and cosmic rays. The frequency range around 3 kilo to 300 gigahertz is called the radio frequency. So the radio frequency range, usually it is from 3 kilohertz to 300 gigahertz. So this is called the radio frequency. It includes many different types of radio communication like AM radio, FM radio, microwave, radar, television, etc., and the wireless. And here is a proper photo, a proper diagram for the electromagnetic spectrum. You can see here the electromagnetic spectrum, which ranges from 3 Hz to 30 EHz. As the frequency increases, lambda decreases. When the frequency is 3 Hz equals 3 Hz, the wavelength equals 10 power 8 meter. And when the frequency is 30 EHz, the wavelength equals 0.01 nanometer, which is 10 power minus 9 meter. So you can see here, as the frequency increases, the number of oscillations and number of cycles per second increases. Here we have the radio frequency spectrum up to 300 gigahertz. We mentioned that the radio frequency spectrum is from 3 kilohertz till 300 gigahertz. So from 3 kilohertz up to 300 gigahertz. This is the radio frequency spectrum, all this. And it includes the millimeter wave. The millimeter waves, which ranges between 30 gigahertz to 300 gigahertz, will be used in the 5G communication system. This is used in 5G communication system. And the terahertz, which is between 300 gigahertz to 3 terahertz, this terahertz band will be used in the 6G communication system. Okay? Then we have the visible light, ultraviolet, X-ray, and gamma ray. So, one of the two main frequency ranges used for wireless and LAN communication lies between 2.4 and 2.4835 gigahertz. This is usually the 2.4 gigahertz. So the 2.4 gigahertz, this band is not a single frequency. This band is a group of frequencies from 2.4 to 2.4835. So this 2.4 gigahertz band, it is not one frequency, it's a group of a frequency which ranges from 2.4 to 2.4835. Even though it does not include the entire range between 2.4 and 2.5. It does not include all this range, but it is It starts at 2.4 and ends at 2.835. Whereas the 5 gigahertz band, it is also a group of a frequency which lies between 5.15 and 5.85. But it does not include all the bands also between 5.15 and 5.85. It only includes these 4 separate bands. So these bands are not continuous. You can see between 535 and 5.47 there is this connection here. So the 5 gigahertz bands, it includes all these 4 bands. Most of the 5 gigahertz bands are contiguous, مجاورين لبعض يعني, except for a gap between 5.35 and 5.47. At the time of writing this gap exists and cannot be used for wireless communication. Let us speak now about the ISM band. What is the ISM? Who knows what does ISM stands for? What does ISM stands for? ISM, the ISM, it is the industrial, scientific, and medical. So it stands for industrial, scientific, and medical. It is open frequency. Open frequencies. That includes the Wi-Fi range 2.4 and 5 and LoRa. LoRa is a low power, long range communication protocol. So LoRa is a low power, long range communication protocol, which include these frequencies: 415 mega, 868 mega, and 915 mega. So LoRa is a low power, long range communication protocol. So the ISM bands, it includes these bands because these frequencies are used in industrial, scientific, and medical. What is the advantages of these frequencies? These are free bands. There is no license required to use the Wi-Fi frequencies. You can use it at home, you can use it at work without having license. It is free to anyone. But the disadvantage is that because there are many users using it, because the license is free, no license is required, and many users are using it, interference will happen. So interference will result because many users are using it. Second, there is low data rate because there is congestion on these bands. Many users are using it and it's for free. So the advantages is that there is no license required, free to anyone, but at the same time there is disadvantage which lies in interference and low data rate. So let us go back to the 2.4 gigahertz band, which is used in wireless. Frequency bands are divided up into a number of channels. So this 2.4, we mentioned that it starts from 2.4 to 2.4835. Okay, from 2.4 to 2.4835. So this band, which is used for 2.4 gigahertz band, is divided into 14 channels. Is divided into how many channels? 14 channels. Each channel is about the width of each channel. The width of each channel is 22 megahertz. So the width of channel 1, channel 2, channel 3, channel 4, channel 5 up to 14 is 22 megahertz. 11 megahertz from the left and 11 megahertz from the right. So this channel, let me draw it by pen. The width of this channel is 22 megahertz, 11 megahertz from the left and 11 from the right. This is the width of each channel. It's 22 overall, 22 megahertz. Similarly for other channels, for channel 3, 4, 5, 6, up to 14. Their width is 22 megahertz. And they are separated with a guard band equals to 5 megahertz. They are spaced 5 megahertz apart to avoid overlapping between channel 1 and channel 2. So each channel, you can see it has its own frequency. And a user can use a channel for wireless communication, can use channel 1 or channel 2 or channel 6 or any channel from this. But we need to make sure that the signal bandwidth is less than the channel bandwidth. What is the signal bandwidth? The signal bandwidth, it is the bandwidth from here to here. We have taken in the previous lecture that the bandwidth is the difference between the upper frequency, f2 for example, minus lower frequency, f1. So the bandwidth is f2 minus f1. It's the difference between the upper frequency and lower frequency. This is the bandwidth of a signal. So the actual frequency range needed for a transmitted signal is known as signal bandwidth. What is the signal bandwidth? It is the actual frequency range needed for a signal to be transmitted. So from its name, it refers to the width of the frequency space required within this band. Okay, this is the signal bandwidth. So if I have signal, if I'm transmitting signal on channel 1 and signal on channel 2, I need to make sure that the bandwidth of these signals from here to here, bandwidth of signal 1, and from here to here, bandwidth of signal 2, I need to make sure that the channel bandwidth of these signals is less than the channel bandwidth. Otherwise, if we have a scenario like this, the bandwidth of the signal is higher than the channel width, the bandwidth of signal 1 is higher than the channel width, and the bandwidth of signal 2 is higher than the channel width, overlapping will occur between these two signals. I will have overlapping between these two signals. So I will have interference. So I need to make sure that the bandwidth of each signal does not exceed the channel width. The bandwidth of signal 1 should be less than the channel width, and the bandwidth of signal 2 should be less than the channel width to avoid overlapping. Otherwise, I can transmit at channel 1, and the second signal I can transmit it, for example, at channel 6, because they will not interfere with each other. At channel 1, 6, and 11, if I use these channels, channel 1 and 6 and 11, no interference will happen, no overlapping will happen between signals. So this is F2 and F3 frequencies. Are so close. F2 and here you mean F2 and F1 frequencies. F1 and F2 frequencies are so close. Okay, so the signal that uses a channel 1 overlaps with the signal that uses a channel 2. There is overlapping between them because they are neighbors. They are next to each other. So always use different frequencies to avoid interference and keep a distance between the channels. If you are using a channel 1 for first user, use a channel 6, for example, for the second user. Don't use neighboring channel, because if the signal bandwidth is higher than the channel width, I will have overlapping. Like you can see here in this figure. The bandwidth for signal 1 and bandwidth for signal 2 are higher than the channel width. This is why I have overlap between these two signals. Ideally, the signal bandwidth should be less than the channel width. So this is what I was explaining. The signal bandwidth from here to here, from here to here, this one, signal 1 bandwidth, should be less than the channel width, so that a different signal could be transmitted on every possible channel. If I have this true, if the signal transmitted on channel 1 is its bandwidth is less than the channel width, and the signal transmitted on channel 2 and 3 and 4 and 5 and 6, their bandwidths are less than the channel width, then I can use every channel for transmission. I can use all the channels for transmission with no chance that two signals could overlap and then interfere with each other. Because I have this true, I have this constraint valid, this condition valid. The signal bandwidth is less than the channel width. But if I have it like this figure, the bandwidth of the channel is higher than the channel width, is bigger than the channel width, then for sure I will have overlap if I transmit it on two contiguous signals, two contiguous channels. Here I need to select different channel. So when the signal bandwidth is wider than the channel assignment, like you can see here, signals will overlap each other as shown in figure 7. Because of this, signals on adjacent channel cannot possibly coexist without interference, without interfering with each other. Signals on adjacent channels, channel 1 and channel 2, cannot possibly coexist without interfering each others. I cannot send a signal on channel 1 and then use a channel 2 for transmission also, because the signal bandwidth is higher than the channel width. So this is the only reason. So signals must be placed on more distant channels. I can use a channel 1 and channel 6 and channel 11, for example, to prevent overlapping, thus limiting the number of usable channels in the band. Here comes the role of the guard band. What is the guard band? In order to prevent interference between channels, unused frequency bands called guard bands. They are used to separate the channels. So what is the role of the guard band? Is to separate the channels, to avoid interference. So this is the guard band between channel 1 and channel 2, between channel 2 and channel 3. There is also guard band between channel 3 and channel M. The advantage is that it prevents interference between channels. So what is the disadvantage? It consumes bandwidth. If I need to use all these guard bands, then I will consume my system bandwidth. In summary, signals must be placed on more distant channels to prevent overlapping, therefore, limiting the number of usable channels in the band. Okay, I will stop for here for today. Then we will continue on the next lecture, inshallah. Wassalamu alaikum wa rahmatullah wa barakatuh.